Hi there, welcome back again. In this video, we'll be doing our sample problem for the flexural members. Okay, so the problem is we are to determine the design capacity of an A36 steel, and the section is S shape 610 by 119, and it is used in a simply supported beam. And this figure shows the length of the beam. So you see that there's no brace, there's no lateral bracing. Therefore, this will be our unbraced length. And it says that um, the support is just simply supported. Okay, so the first step is to obtain the necessary information. Obtain the necessary information. Okay, and where do you get this? That's from section property table. Section property table. And what we get is our area is 15,200 mm squared, and we'll also need our width of flange, which is 178 mm, and the thickness of web, which is 12.7. Also the thickness of the flange, which is 22.1 mm, and we'll also need our radius of gyration. That's 241 mm along the x. I don't know if we need the radius of gyration along the x or y. And I'll just write it here. This is 34 mm, and we'll also need our section modulus along the x, 2,870 times 10 to the 3 mm cube. Okay, so take note that for the section modulus, it's given, the values given is just this, but you will notice that in the table it says it's raised to times 10 to the 3. Okay, and what else? We'll also need our plastic section modulus, 3,340. So that's going to be times 10 to the 3 mm cube. And we'll also need our compact section. So this one, the flange, this is equal to 4.0, and our web element, sorry, this is flange. Okay, so TF. So this one is the web element. That's 42.1. Okay, so I guess we can now proceed to the next step, and that's to determine the slenderness. Okay, so the first one is, let's check the slenderness of the flange element. Okay, so we have this symbol, the width to thickness ratio, and it's just simply BF all over to TF, which is just 4.0. And our limiting width to thickness ratio, lambda sub p is equal to 0.38 square root of E all over Fy. Okay, so for our Fi, that's 250 megapascals, and this one is 200,000. Okay, so 200,000 divided by 250, take the square root, okay, times 0.38, and that's 10.7, let's say 10.75. And our lambda sub r, the limiting width to thickness ratio for the slender elements. This one I think is for the compact section or non-compact section. And this one is for the slenderness. This one is 1.0 square root of e all over Fy. That's just 28.28, and we see that lambda slenderness of the flange, I mean the width to thickness ratio, is less than lambda sub p, and which is also lambda sub r. Therefore, flange flange is compact. So flange is compact. Okay, so the next step is to check the slenderness of the web element. Okay, our lambda is h all over is hc all over t sub w, and that's from the table. The value is 42.1. 42.1, and our limiting value, okay, let's start with lambda sub b, is 3.76 square root of e all over Fy, which is just times 3.76, that's 106.35. This one, the limiting value, this is 5.7 square root of e all over Fy. This one is 20 square root of 2 times 5.7. This is 161.22. So we see that this lambda is less than lambda sub b, is less than lambda sub r. Therefore, web is compact. Okay, so therefore, we can proceed to our calculations, because we only discussed the topics on strength, strength of flexural members having compact sections, both compact sections and double symmetry or channels span about their weak, not the weak axis, bend about the strong axis. Okay, so because we know that the flange is compact and the web is compact, then we know that the governing, let's write it here, therefore the governing limit states are yielding and lateral torsional buckling. Okay, so let's check now the yielding. Okay, so solving for nominal strength. Based on yielding. Okay, so our equation is just m sub n is equal to m sub p, the plastic moment capacity, is equal to the yield strength of steel times the plastic section modulus. Okay, and this one is 250 megapascals. okay, times our plastic section modulus is 3,340. 3,340. Okay, so don't forget that times 10 to the 3, that's in mm cube. Okay, so 250 times to the 3, and we obtain this value, and our unit, if we use this value, our unit would be Newton. Okay, so we have this Newton per mm squared. This one is mm cube, so we'll have a unit of Newton mm. But for moment, we usually use the units of Newton meter or kilonewton meter. So let's say we want a value of kilonewton meter. So therefore, we will divide this by 1 million. That's 835 kilonewton meter. Okay, so that's our nominal moment capacity based on yielding. Okay, so the next step is step number 4. Let's solve. From here onwards, we will be solving for the lateral torsional buckling. But before that, we have to check for the brace length and the limiting values. So calculate the limiting value for the length, or unbraced length. Okay, unbraced length. Okay, so L sub P. L sub P is we can solve this L sub P by 1.76 R sub Y square root of E all over Fy, and our R sub Y, that's 34. This one is 20 times square root of 2. Okay, times 34 and times 1.76. We have that's in mm, so we have 1. You can just convert that to meter, so 1.69, and our L sub R is pi, then this parameter times the square root of E all over 0.7 Fy, and we need to solve this first. RTS is equal to the width of the flange all over the square root of 12 times 1 plus h, the thickness of the web, divided by 6, and then the width of the flange times the thickness of the flange. Okay, so this is our equation. Okay, so we'll check if we have a value for the width of the flange. Okay, so yes, we have. Then thickness of the web, thickness of the flange we have, except for h. Okay, h is actually let me draw it here. It's not actually the depth. It's different from the depth. If this is the depth d from the table, the h value is actually there is a fillet here, or a root so therefore it's lower than this. That's gonna be our h. So for our h, I guess we can solve this using this relation. Okay, so h sub c is, all over the thickness of the web is 42.1. So if we have the thickness of the web, then I guess we can solve for this. So h is 42.1 times the thickness of the web, which is 12.7. This one in mm. 42.1 times 12.7. That's 534.67 mm. I guess that makes sense because we have a depth of 610. So if this is 610, then of course this one should be lower than 610. Okay, so now let's substitute the value. R, sorry, this should be R sub ds. This one should be subscript. So what's the thickness of the flange? That's 178. And we have square root of 12 times 1 plus the h, 534.67 times the thickness of the web, which is 12.7 all over 6 times the flange width, that's 178, times the thickness of the flange, which is 22.1. Okay, so if you check the units, that's all in mm. Okay, so now let's solve this. 12.7 times 534.67 divided by 6 times 178, times 22.1, and we add this plus 1, okay, times 12, and we take the square root, then 178 divided by the answer, we get a value of 45.28. So 45.28, this is in mm, and mm, so the units in the denominator cancels out, so this is just mm. Okay, so now we have this, then we can substitute the value in this LR equation. So pi times 45.28 times square root of E, which is 200,000. Then this one would be 0.7 times the value of the Fy. Okay, times pi times the square root of 200,000 over 0.7 times 250. And we have 4,809. That's in mm. Okay, or 4.81 meters. Okay, so our unbraced length, our LB is 6 meters. Okay, so 6 meters. And we see that our LB, or we can write it backwards. We have this L sub P, the limiting value, which is less than the limiting value for the slenderness, and our L sub B is right here. Okay, so the L sub B is 1.69, then this one is 4.81, and this one is 6 meters. Okay, so if this is the case, then our equation our equation for the nominal moment capacity based on lateral torsional buckling is m sub n is equal to FCR times the section modulus, but it should be less than our plastic moment capacity. Okay, so this is our equation. Now we have to solve for, that's right, this is step number 5, solving for the critical stress FCR. FCR is equal to the moment rigid factor times pi squared times E all over the unbraced length divided by RTS. This is squared. Okay, this one, just assume it is 1.0, and pi squared times 200,000 megapascals. And this one is base length 6 meters. Okay, this one is in mm, so therefore let's use 6,000 and divided by 534. Sorry, this is 45.28. Okay, so 45.28, and we square the denominator. Okay, so pi squared times 200,000, okay, divided by 6,000 all over 45.28, that's squared. We get a value of 112.42. Okay, we'll check the units. This is megapascals, this is mm divided by mm, so the units would be megapascals. So therefore, we can just write it here. Therefore, the moment capacity based on lateral torsional buckling is Mn is equal to FCR times S sub x, but it should be less than our plastic moment capacity. This FCR is 102.42 megapascals, and this one, the section modulus, is 2,870. Don't forget times 10 to the 3. This one is in millimeter. Okay, so times 2,870, and we divide this by 1 million so that we can get a unit of kilonewton meter. So divided by, we have 322.64. Okay, but it says here that it should be less than our plastic moment capacity, which is 835 kilonewton meter. Therefore, the design strength is the design strength is the lower value of the two. That's gonna be when you say design strength, then meaning that we have to apply the reduction factor, the strength reduction factor. Okay, so VMN is just 0.9 times times this one, meaning that the lateral torsional buckling governs. That's 322.64 kilonewton meter. Okay, times 0.9, that's 290. Okay, so if we review what we did in any analysis problem, especially for especially in this steel structure, we first have to obtain the necessary information which can be obtained from the section property table. So since this is an analysis, meaning that the section is given, so we know the dimensions, and what we'll solve is the capacity of that section. So we obtain the values needed, and then we check the width to thickness ratio, so that we can determine if the flange element is slender or the web element is slender. Okay, so we found out that that the width to thickness ratio of the flange is a compact section. Now this one for the web element is also compact. So therefore, since they're both compact, then we can apply our our equation for the nominal capacity based on the conditions that's given. Okay, so if in your homework it turns out that the flange is not compact, or for example the web is a non-compact, then we cannot apply the equations for the nominal moment capacity, because it's a different computation process. Okay, so for this, we'll just make sure that we have a compact flange and a compact web, and therefore the governing limit states will be yielding and the lateral torsional buckling. So we first solve for the yielding, and it's just straightforward. We just multiply the yield the yield strength to the plastic section modulus. Okay, so our nominal moment capacity is just based on this plastic moment capacity, and that's 835. After that, we solve for the nominal capacity based on lateral torsional buckling. But before that, we have to check first if our unbraced length is whether the unbraced length is below the limiting values, or between or above the maximum limiting values. Okay, so therefore, we first have to check the limiting values L sub P, and we get 1.69. Then we check the limiting values L sub R, and of course there's a lengthy computations here, but after you obtain the L sub R and L sub B, then you have to compare your unbraced length, and it turns out that our unbraced length is greater than our L sub R, is greater than our L sub B. So therefore, the moment capacity would be this one. Okay, that's going to be based on the lateral torsional buckling. Okay, so we have to solve first for the critical stress. We substitute the value, and we obtain 835. No, not this one. This 322.64 kilonewton meter. Okay, so the governing strength would be the lower of the two, and that's the 322.64 based on the lateral torsional buckling, and we multiply that to our strength reduction factor, and therefore this will be our design strength, 290 kilonewton meter. Okay, so I guess that's all. That's all for our topic on flexural members, and in our next video we will be moving on to timber structures. Okay, so I guess we're near the end of this course.